Hi, my time has started. So I'm Adam. I'm going to be presenting Motion Policy Networks, or MPI-Nets. MPI-Nets is an end-to-end policy for manipulation designed to produce collision-free motion to a 6D end effector target. The input to the policy is a point cloud that's segmented and calibrated. Points are labeled with obstacle, target, or collision, or obstacle. And the output is a small displacement for position-based control. It's trained on a large data set, 300 times larger than prior work. The expert is specifically designed to be learnable and consistent across our whole data set. When it's used in novel in-distribution environments, it works about as well as a global motion planner, and it can also generalize to complex real-world geometry such as those dishes. Its end-to-end nature allows it to react quickly to dynamic non-stationary objects. Please come check out the poster for more info. Thank you very much.
Hello, everyone. I'm Le Tianchen. Today, I'm happy to present our work on fast lifelong adaptive inverse reinforcement learning from demonstrations. Our work, FLAIR, enables end users to teach robots, and robots can efficiently personalize their policies, as personalized service contributes to long-term acceptance. FLAIR enables lifelong learning by extracting a policy prototype from unique demonstrations, and when possible, reuses these policy prototypes to form policy mixture to explain a new user's demonstration. We test our algorithm on a real robot table tennis task and personalize to each user that give us demonstration. Here are some examples of our strikes. We let users rate our policy against benchmarks, and we find that users rate our policy to have a higher task score and a strategy score, meaning we are more successful and personalizes better. If you have any question, I'm happy to answer them in our poster for paper 443. Thank you.
Hi, I present LARA for Light and Rays, a general architecture for scene understanding. Here we apply it to a self-driving car with 6 cameras, and the architecture can be split into 3 parts. First, we concatenate a ray embedding to each pixel of the feature maps. This provides information about the 3D position and orientation of each pixel. Then we encode everything into a small collection of latent vector with cross-attention. Then we can query this compact but rich internal representation of the scene to make prediction into whatever space we want. In this case, we do vehicle binary segmentation in the bird eye view space. We obtain SOTA results and also show that a partitioning of the scene across latent vector naturally emerges thanks to our ray embedding. For more details, I will see you in the poster lobby. Thank you.
Hi, my name is Yongshu Yang, and this is our work on the panoramic 3D object tracking via cross-camera fusion. So nowadays, autonomous vehicles are usually equipped with multiple cameras to check the object's full surrounding. Yep, the current camera-based approach only focuses on the single camera setup. So in this way, they will fail to truly track objects moving across cameras and also affect the overall performance of the motion modeling and during training and both inference. So in this work, we propose a new pipeline that to make sure the tracker could check the objects to do the association with the full cross-camera information and also have a better motion modeling. So this is our overview figure. And with our new pipeline, we could outperform the previous state-of-the-art by 40% on the popular nuisance data set. So this is our qualitative results on the new things. And so if you find our work is interesting, please stop by our poster and we can have a further discussion. Thank you.
Hi, I'm Jacob Beck, and I'll be talking about my work on hypernetworks in MetaRL, along with my colleagues at Oxford. So as you all know, RL is pretty sample inefficient. We can't really deploy it as is in the real world without spending tons of money on a lot of robots or like killing a lot of people. Um, so one solution is to generalize over a set of related tasks in order to improve learning on a single task. And in this setting, state-of-the-art that's often called meta-RL or multitask RL. And in this setting, often state-of-the-art can be outperformed just by training a separate model for each task. But that doesn't generalize to new tasks. So in order to generalize to new tasks, we propose using one network to generate the weights and biases for another network. That's called a hypernetwork. The only problem is that doesn't really work. So we propose a simple fix to get that to work. And the results are great. So come check out our poster.
Hi, I'm Daniel from the University of Utah, and I'm introducing our work led by Jerry Hay at Berkeley on assistive robotics tasks by learning representations. We focus on an assistive itch scratching task where we want to train a robot policy that can generalize to new humans at test time. This is challenging because each person has a different and unobserved preference over how much they want to move their arm and where they want to be itched. So how do we accomplish this? We train jointly a representation space as well as a policy over a large population of simulated humans. A good representation then allows us to interact with a new human at test time, embed that interaction into the latent space, allowing the policy to better learn how to assist and adapt to the user's implicit preferences. Importantly, we find that training this latent space to be useful for predicting future human actions is a really important auxiliary loss. When compared to prior work on learning latent spaces, we find that our approach shown here in orange achieves better generalization on out-of-distribution humans. Also, our latent space is easily adapted at test time for better performance.
Hey everyone, I'm Shikhar and I'll be talking about video decks, joint work with Kenny Shah and Deepak Pathak at CMU. Passive datasets have typically been used to learn visual representations, but can we also use them to learn actions? So our approach starts by first taking many different human videos, for example, from Epic Kitchens, as you can see here, extracting visual priors, and merging these with action priors obtained from retargeting human hand trajectories. We use these priors to pre-train a policy on a large set of human videos, and then we fine-tune with a couple of robot demonstrations that we obtained from our previous work on robotic teleoperation learned on YouTube. Let's look at some results. We perform many different complex manipulation tasks and thorough real-world experiments, both with a dexterous hand and a two-finger gripper, as you can see here. For more information, we encourage you to visit our poster in the main lobby area. Thank you.
Have you ever wondered why we as humans are still able to outperform current robots in terms of versatility, robustness, and especially learning of new tasks? Our research hypothesis is that this is mainly due to the underlying actuator morphology, or more specifically, our muscles. My name is Isabel Wochner, and in our study, we showed that learning with muscle-like properties can be beneficial due to three major results. First, we showed that learning with muscle-like properties is more data efficient compared to their torque-driven counterparts. Second, it's also less sensitive towards hyperparameter variations. And third, more robust towards unknown and unlearned force perturbations. We believe that these results are crucial for the robotics community because we can either use them to simulate muscle-like properties directly as low-level actuator control layer on real robots, or implement them in novel soft robotic actuators, for example, in wearable rehabilitation devices. Thanks.
Hi, I'm Christian from the QUT Center for Robotics, and I'll be presenting our work on residual skill policies. Skill-based learning has emerged as an effective strategy to incorporate demonstration data within the reinforcement learning framework. However, exploration through the skills base is still challenging for downstream reinforcement learning, and downstream RL agents are limited to learning tasks within the same distribution as the demonstration data. We propose to learn a latent condition skill prior using normalizing flows. During downstream RL, we can use the skill prior to map sampled exploratory actions towards the relevant regions of the search space. To adapt to a wide range of task variations, we introduce a residual policy which gives our agent access to the atomic action space to adapt the skills to task variations. This results in accelerated learning for downstream RL tasks and the ability to learn downstream tasks with a wide range of task variations. Thank you.
Hi, everyone. I'm going to talk about versatile imitation learning and more precisely about learning from human demonstrations. So the first thing that comes to mind when we're learning from humans is that they solve tasks in very different ways, with even simple tasks often resulting in very, very complex distributions of a behavior. While other work at CoRL focuses on improving what the human sort of demonstrates to the learner, we here instead want to leverage this, want to lean into it and learn from few human demonstrations while capturing this versatility. We do this by, well, using human demonstrations and then from them encoding some geometric descriptors, which you can think of as some encoding of task-relevant features. We then do the same from samples from Gaussian mixture policies, training a discriminator on both of them and then using this discriminator to update the policy. This is iterated over until convergence. Our experiments include real robot experiments with human data in a teleoperation setup. And our results show that we are able to accurately model complex distributions over behavior from just a few demonstrations. Please check out our post and thank you.
Hi, my name is Oyer, and I will present our work on latent plans for task-agnostic offline reinforcement learning. In order to scale robot learning, robots should ideally be able to efficiently learn from offline diverse data sets that might contain a broad range of undirected behaviors. CoRL makes sense of this data by combining the strength of imitation learning and offline RL to learn task-agnostic long-horizon policies. We combine a low-level policy that learns latent skills via imitation with a high-level policy trained with offline RL that skill chains latent behaviors. Our hierarchical approach effectively reduces the horizon of the high-level policy and solves up to 25 long-horizon visual motor tasks in the real world by stitching together latent plans via goal chaining. If you're interested in learning more about this, come check our poster.
Hi, I'm Peter from NVIDIA. DivStack is a new architecture for autonomous driving that is differentiable and modular at the same time. The key idea is to make the existing stack differentiable, including its fixed algorithmic components like planners and controllers, and then train everything jointly end-to-end. This way, we are combining the generalization, interpretability, and safety guarantees from the standard stacks with the task-oriented training of neural network policies. So concretely, in this work, we are using a learned motion prediction model, a handcrafted planner, and a differentiable MPC controller. And then we are training for a combination of prediction loss and end-to-end losses. Our key result is that by training the prediction model end-to-end, we get a similar prediction accuracy, but much better driving policy. Why? Because we are optimizing everything directly for what ultimately matters for driving. So as we all know, the answer to life is 42. This poster is in room 41. Thanks.
Hello, my name is Philip, and I'm here with my co-author Alejandro today to present our work Daydreamer, where we learn robot policies from scratch directly in the real world. We do so using the Dreamer algorithm and use the same hyperparameter across tasks. We do this on a variety of tasks, such as quadruped walking and visual pick and place. Here you can see a run of the quadruped learning how to walk in an uncut video that's sped up. And after about an hour's training time, we're able to recover this type of walking policy. Now, after an additional 10 minutes of training, where we are constantly pushing over the robot and perturbing it, we can now train the robot to have this really robust walking policy, and it's able to recover despite being pushed over. And this dynamic recovery is personally really impressive to me. So if you're interested in learning more about how we do this, please come by our poster session. Thank you.
Good morning, everyone. I'm Xiaohong from Oxford, and today I'm presenting our work touching a nerve. So as we all know, tactile sensing is important in robotics. However, collecting tactile data is expensive and painful process, and the data sets are usually sensor specific. Thus, we want to be able to generate these tactile sensor responses. we propose a simple approach combining nerves and conditional GANs. So specifically, what we do is we use nerve render RGBD images as inputs to a conditional GAN model to generate the sensor responses of a digit tactile sensor. And our method shows benchmark between qualitative and quantitative results in simulation and real world, and it handles 3D objects and rotations and generalizes new objects and viewpoints. We also show the framework is able to transfer to a new sensor with a small fine-tuning data set. And our method is also useful in a downstream tactile object classification task where we increase accuracy by around 10%. And do please come check our poster. The paper number is 326 and the room is 40. Thank you.
How can robots leverage multiple types of queries when learning from people? Demonstrations are one type of query, but there are others that a robot can use, such as proposing multiple actions and the teacher indicates their preference. A robot can instead propose one action, which the teacher then corrects by offering an alternative that better completes the task. Or the robot can simply ask for an evaluation of its proposed action. Overall, a robot can learn from any one of these query types, but they all differ according to what information the robot needs to propose and the constraints on how the teacher may respond. Prior work has shown how to optimize a robot's queries within each query type. But what about allowing the robot to choose what type to use in the first place? We contribute a model of information gain that is generalized across all 4 query types. Our approach enables faster, more robust learning than typical heuristics for selecting queries, while also allowing us to balance the informativeness and cost of queries. Come visit us at poster room 40. Thank you.
Hi, we would like to present a model called JFP, Joint Future Prediction, which predicts multi-agent future trajectories jointly. This diagram shows a limitation of marginal models, which predict future distribution per agent independently. Let's assume that each of agent A and B have equal probability of turning left and going straight. However, it is very unlikely that agent A turns left while agent B goes straight. But marginal models cannot represent that this is unlikely. So JFP is using a pairwise graphical model to represent joint probability. The baseline model in the first row make predictions which have collisions marked in red. The second row from the prediction from JFP do not have collisions for the same scenes. JFP is on the top of a Waymo open motion dataset interactable leaderboard with the large margins. Please visit us in the room 40B. Thank you.
Hi everybody, my name is Guillaume Sartredi and I'll be presenting our work CATNIP, Context-Aware Attention-Based Network for Informative Path Planning on behalf of my student Hugh Hong, who sadly couldn't get his visa in time. Our work addresses the IPP problem where a mobile robot is tasked with building a belief of a given quantity of interest over a bounded domain such as temperature, radiation, or Wi-Fi signal, within constraints over its total path length and number of measurements. We first formulate IPP as a sequential decision-making problem on a randomly generated graph and allow the agent to learn a subtle representation of its entire belief, which it then uses to reactively plan its path. In doing so, our agents learn to sequence local decisions informed by its global belief over the entire search domain to better balance the exploitation of known high-interest areas and the exploration of unknown areas. In our experiments, we show that CATNIP significantly outperforms state-of-the-art conventional planners in terms of solution quality and computing times. We also validate CATNIP on a simple light-based IPP scenario. If you're interested in our work, please come by our poster in room 40B. Thanks a lot for your attention.
Good morning. This is Yiting. I'll present our work, learning role scene representation via semantic region prediction. We tackle driver intent prediction, risk object identification from egocentric images for vision-based intelligent driving systems. The task is challenging because we have to extract meaningful or useful information from high-dimensional inputs. We invested the question, what would be the good representations for the two tasks? So our proposal is semantic region, a new representation that capture semantic and geometric cues of traffic scenes while ego vehicles taking afforded actions from their to their destinations. Different examples of semantic region are shown on top of the posters. And we formed a new task called semantic region prediction. We show that the learned latent representation are effective for the two tasks compared to other forms of representations. We also show that they entail favorable generalization capabilities when tested on scene data set. Please stop by our poster section. I will explain more detail. Thank you.
Hi, super excited to share our work in Sim2Real on one of the most visually complex domains to date, off-road autonomous driving. To bridge the visual gap, we convert RGB images to segmentation maps, which are concise and shared across visually distinct domains. Our approach consists of two main phases. First, training a segmentation model from simulator data, and second, training an RL agent. We can then deploy zero-shot to the real world. Even when real-world environments look drastically different from our simulator environments, the segmentation space is familiar for the agent. We use the Unity simulator, including 3 diverse domains with forests, canyons, and meadows. We do not model any of our environments from real-world environments. Our segmentation model is trained on this diverse simulator data, and we train our agent in these distinct domains. Sim2Real is never complete without real. We evaluate both offline and online. We see impressive segmentations from a model that has never seen real data. We are able to match expert behavior and reach goals efficiently from offline data, and we can run successfully on unseen terrain. Thanks, and hope to see you at our poster session.
Hi, everyone. I'm Jing Tang. I'm glad to share our work casting robust and scalable in the wild 3D reconstruction. So here, our goal in this paper is based on, given the sensor observations, our goal is to reconstruct the 3D assets in 360 degrees, and then we use it for the realistic and controllable simulation, and finally test our autonomy system. Our approach is able to reconstruct all the nearby vehicles at scale with high fidelity. And with this assets, we can do more camera and LiDAR simulation. So here you can see we manipulate the vehicles and the wheel is also spinning. And we can even do more by generating the safety critical scenarios. And more importantly, we can generate those interesting snippets at scale. Our approach can also build the relations between our reconstructed assets. And so basically it's naturally support us to doing the text transfer in the real world. So here it can enable us to enrich our asset bank and doing more with our asset approach. And also we can doing more asset reconstructions at larger scale. And please come and check our poster. Yeah, thanks for your attention.
Good morning. My name is Nate, and I'll be presenting on behalf of my colleagues at Princeton. The work is titled Leveraging Language for Accelerated Learning of Tool Manipulation. Consider the description of common tools such as a pair of tongs or a spatula. Notice that these descriptions contain information about the perceptual features and affordances of the tools. In this work, we explore using that information to better enable a robot learning to use a new tool. The approach is titled ATLA, Accelerated Learning of Tool Manipulation with Language. In this approach, we use ChatGPT to automatically generate diverse language descriptions of the tools, and then we leverage meta learning to train a downstream task policy conditioned on those generated descriptions. We show an improved performance in learning over a variety of tasks, including pushing, lifting, sweeping, and hammering. And we hope that you will join us at the end of the poster lobby to ask any of your questions. Thank you very much.
That's it for the spotlights. Next up is coffee break at 10:50, and please be back here for the orals at 11:20.